Hi, this is Professor Evans. This video is for EET 1214C, which is Intro to Engineering Technology at Valencia College. And in this video, we are going to get an introduction to digital circuits. So first, let's begin with our learning objectives. By the end of this video, I hope that you will be able to define the voltage levels of a digital circuit. I hope that you'll be able to describe the truth table, the symbol, and the expression for and, or, and not gates, and that you'll be able to evaluate the output of and, or, and not gates using multisim and on the bench. Now this last bullet here will be covered in 2 separate videos that you can find on my YouTube channel. As we go through this video, please remember to have your lecture notes out and to fill them in along with me as we talk about digital circuits. So let's first start with the definition. Digital circuits, like the kind you find in a computer, the kind that you find in all of the sensors in your car, all the electronic equipment or electronic devices that you use in your everyday life, all have digital circuits in them. And we define that as a circuit that requires only 2 voltage levels, 0 volts or 5 volts. When we talk about digital circuits, 0 volts represents what we call a logic 0, and another word for that is called low. And 5 volts represents a logic 1. Another word for that is high. So we're going to have a couple of interchangeable terms that basically stand for one of 2 states, a 0 volts or a 5 volt state. This unit is just a taste of what digital circuits are all about, and you're going to get more details on different types of logic circuits when you advance to your digital systems courses, which at Valencia College would be CET 2114. So this unit is just a little snippet and an introduction into what that course will go into later. For now, we're just going to talk about the basic operations performed by logic circuits. And again, we're talking about circuits that only require 2 voltage levels, either at the input or the output, 0 volts and 5 volts. This is an example of a digital circuit on the left. Each one of these shapes here represents a certain logic function, and we call them a gate. So for example, this is an AND gate. It's a circuit that has a particular function, and we're going to describe what those functions are in just a few slides. The inputs to our circuit are on the left. Each input has a name, so I have 3 inputs A, B, and C. Because this is a digital circuit, I know that the value or level that is going to be connected to inputs A, B, and C is only ever going to be 0 volts or 5 volts. We can see that the different gates are connected, and we have an output on the right called Q. That output, again, will only ever be 0 volts or 5 volts because this is a digital circuit. So we only have 2 possible states, on or off, high or low. So when we look at the output of a digital circuit, we might have something like a square wave. As the inputs change, the outputs will change. And those outputs will only ever be high, 1, closed, on. So all of these are interchangeable terms to describe one state. The second possible state is that the output could be low, 0, open, or off. So all of these words on the bottom correspond to the same idea of 0 volts. All of these words on the top correspond to the same idea of 5 volts. So we have a lot of interchangeable terms, but at the end of the day, a digital circuit only has 2 states, 0 volts and 5 volts. And a digital signal is what comes out of a digital circuit, and that signal will only ever have one of 2 possibilities. Either the signal will be high, 1, closed, on, or the signal will be low, 0, open, off. Those are our only 2 possibilities when we look at a digital circuit. So now let's learn about what these symbols mean. So I'm going to break each one of these down. Each one of these performs what we call a logic function, and the first one we're going to talk about is the AND gate. All right, so logic circuits operate based on the following 3 fundamental functions. So if you think about all of the electronic devices that you've used today, all of the microcomputers, microprocessors that are in those devices, all of the computer programming that has gone into those devices, it all boils down to 3 basic concepts at its most fundamental level: and, or, and not. So let's talk about and. First, you'll see on the screen we have a truth table and a symbol. All right, so the truth table describes how the AND gate is going to operate. The symbol is what the AND gate looks like when we draw it on a schematic. The AND gate has two inputs, A and B, and it has an output that we're going to call X. The truth table tells me if A and B have certain levels, either 0 or 1, what's the output going to be? So the truth table is like a roadmap that describes exactly how that circuit is supposed to work 100% of the time. So when I think about the idea of AND, here's an example. If you have a clothes dryer and you want the dryer to turn on only if the timer is set above 0 and the door is closed, we basically have a situation where we only want a situation to occur when two things happen and they both must happen. That's the idea of AND. If we look at the truth table for AND, we can see that the values of input A and input B are changing. We have two inputs, and because this is a digital circuit, the value of those inputs can only ever be 0 or 1, high or low, 0 volts or 5 volts. So that means we have four possible combinations for the inputs to our AND gate. A and B can both be 0 or 0 volts or a low. And if neither one of these things happen, then the output is a 0. If A is 0 while B is 1, the output is still a 0. If A is 1 while B is 0, the output is still 0. And then if A is 1 while B is 1, we get a 1. See, this last row here describes the idea of AND, the fact that two events must happen in order for the output to occur. In order for the dryer to turn on, the timer must be set. So consider this is our timer being set. And the door must be closed. When both of those things happen, our dryer turns on. So when we write a truth table, we typically show the inputs and the outputs of that particular circuit. We show every possible combination of inputs. We show what the output is supposed to be based on the inputs. And we also write each input as 0 and 1. But remember, 0 and 1 represent 0 volts and 5 volts, those two distinct states of any digital circuit. So this is our truth table that you want to write down in your notes. This is your symbol. And then the last thing is the expression. Anytime the operation AND is used, it's represented with a multiplication symbol. So you'll see the output is written here as X equals AB. Now, we're not saying A times B as if this was an algebra class. We're using multiplication to represent what AND means, but we're not saying that A is multiplied by B. We also have the expression written right here, but again, the way I would read this in a digital systems class is X equals A and B. I'm not saying X equals A times B. Even though that might look like what's happening here in the circuit, we are not multiplying these values together. The multiplication is just a representation of AND. It is not physical multiplication of values. So the expression that we use for AND is multiplication. So the way that we can think about AND is the output is high when all of the inputs are high, or we can say that the output of the AND gate is low as long as any input is low. Either way you want to think about that, that is how we remember the definition of AND. Now let's talk about OR. This is our second basic operation. So think about an oven light. Let's say that you want the light to come on if the oven door opens or if the oven light switches on. So we want something to happen as long as at least one of these two things happens. Here's our symbol and truth table for OR. Notice this symbol is curved and looks more like an arrowhead, whereas the AND gate was flat on the left and looked more like a D. So we have our two inputs for OR. And again, we have our truth table showing all possible input combinations. A and B can both be low. A can be low while B is high. A can be high while B is low, or they both can be high. Those are our only four possibilities. And on the right, we have the output for each, set of inputs. So we can see here that as long as at least one of these things happens, as long as A is high or B is high or both of them are high, the output is going to be high. And we say that an OR gate produces an output of 1 as long as at least one input is high. So with an OR gate, we're going to get that high output as long as at least one of the inputs is high, or both. Notice this time with the expression, we use a plus symbol to represent OR. So again, the output of this OR gate here is called output X, and I would say X equals A or B. It's not A plus B. If you look over here at the truth table, I usually get students who say, well, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1. Why isn't 1 plus 1 2 right here? Well, that shows that they're thinking about that plus sign as addition when that's not what plus means in a digital realm. Within the digital world, plus means OR. So I'm not saying 0 plus 0 equals 0. I'm saying 0 or 0 equals 0. Because in the digital realm, we only have two possible options, 0 or 1, high or low. We don't have the number 2, for example, in our truth table because there's only two options. Either it's 0 or it's 1. So we have 0 or 0 equals 0, 0 or 1 equals 1, 1 or 0 equals 1, and 1 or 1 equals 1. That's how we want to think about the idea of OR when we think about that plus symbol. So let's compare AND versus OR. The AND symbol has the flat edge. It's curved like a D. 2 inputs, 1 output. And the AND output will only go high when all the inputs are high. The OR gate is curved on the left and has more of an arrowhead shape on the right. 2 inputs, 1 output. The output will go high when any input is high. So those are our differences between AND and OR. Our last gate is NOT. This is the symbol for NOT. It has 1 input and 1 output. When the NOT operation is used, the output will be the inverse or the complement or the opposite of the input. So another word for a NOT gate is an inverter. It inverts the input. So if we look at the truth table for NOT, if a 0 goes in, a 1 comes out. If a 1 goes in, a 0 comes out. It literally takes whatever is coming in and flips it to the opposite. We call that an inverter or a NOT gate. Notice the symbol for a NOT gate is a triangle with a little bubble at the end. The bubble is very important not to forget when you're writing it. So make sure that you have both the triangle and the bubble. That's part of the symbol. And when we read the expression for a NOT gate, we could say that X equals not A. We could say X equals the inverse of A, or we could say X equals the complement of A. All of those things represent the idea of an inverter or a NOT gate. So, like I said, the NOT gate is also called an inverter. Notice that the expression, this is the expression here at the output. The expression here is X equals A with this little bar on top. We call that an overbar. So anytime that something has been inverted by a NOT gate, you're going to write that particular variable with an inversion symbol or the overbar on the top. So now let's put this all together. What can we do with AND or a NOT gates? Here's a simple example. So let's say that you're designing an alarm system and you want the alarm to go off if the door and the window are open, or the door and the garage are open, or the window and the garage are open. So let's say that I represent the door, the window, and the garage each with a sensor. The sensor can send a signal whether those particular elements are open or closed. Let's say that the garage is sensor A, the window is sensor B, and the door is sensor C. Here's my circuit that would sound my alarm using some AND gates and some OR gates. If the door and the window are open, so let's say that I connect my sensor for the door and the window to an AND gate. If both of these are open, let's assume that open means I'd have a 1 and a 1. If both the door and the window are open, I'd get a 1 coming out of this AND gate. If the door and the garage are open, so see here I have a second AND gate, with the sensor for my garage connected here and the sensor for my door connected here. So now I'm comparing the door in the garage to see if they're open. With the last AND gate, I'm comparing the window in the garage because I've got one input connected to A, one input connected to B. So if this happens, or this happens, or this happens, I want the alarm to sound. So I've connected the output of each one of these AND gates to an OR gate. So this OR gate will give me a 1, and imagine that that 1 would sound the alarm if this happens, or this happens, or this happens. So this is a simple example of what digital circuits are used to accomplish. When we have a logical system that operates off of things like AND, OR, and NOT, we can use these different gates to implement those functions. So that's the end of this first video with just a basic introduction of what AND, OR, and NOT mean. Please contact me with questions using my email address, Canvas if you're one of my current students, or comment on this video and I will send a response.